I want to spend a good chunk of time going through the 4 models of adoption that we introduced on Monday. These are all models of how behaviors, ideas, disease, whatever you want to consider, is adopted by a population. So if it's a behavior, it's taken on, if it's a product, it's bought, if it's an idea, it's believed, if it's an infection, it's infected people, okay? So we start off with the broadcast model, which is the basic one. Can someone give you an idea, when does a broadcast model apply? And you might be able to guess by its name. Yeah?
When information, or I guess something that you can have or not have, is spread over, like, to the masses, over like a broad spectrum, like a broad way of disseminating information.
Exactly.
And, like, other things.
Perfect. So there's like a megaphone that gives the information about this product exists, or there's this great thing that you can do that everybody gets. It's broadcast, as opposed to what we see later when the information behavior goes from person to person, right? So cool. And so in our broadcast model, we have a few coefficients. We have the broadcast coefficient, or a few items we need to know. The broadcast coefficient. This is pretty much just, from 0 to 1, how quickly something is adopted. There is N, the population of eventual adopters. This is really important. N is not the entire population. It's this number of eventual adopters which exists in reality, even though we might not know what it is. Does that make sense? Yeah. And then there is the number of people who adopted at time t. Great. Just kind of go over how it works. So in every period, we have, we see our broadcast coefficient. What's this in layman's terms? So big N minus N sub t.
Delta N.
People who have adopted it.
Yeah, people who have not adopted it.
No.
What did you call it?
I said Delta N. That's not very layman.
All right, but that was in layman's terms. Okay. People who have not yet adopted yet among all eventual users, right? Okay, great. So not the total population, but okay, great. Yeah.
When you say eventual, do you mean everyone in that group will eventually adopt it, or there's potential for them to adopt it?
No, they actually will eventually adopt it.
Everyone?
Yeah.
Okay.
No, not everyone. So
Everyone within that population.
right, exactly. So there's, in New York City, there's like some, there are 8 million people in New York City. This great new kind of, or 1 million women, and there's this great new like hair bob thing that comes up that we know that this percentage of women are eventually going to adopt. This bunch of women are going to have nothing to do with it. So this is our N. Right, so it's not all women, it's just those women who we know eventually are going to have that haircut. Sorry, my examples are not as cool as your pages. Okay, but this makes sense, right? Cool. And then the number of adopters in the next round is simply new adopters plus old adopters. Great. So now this is something that, well, this example we could actually turn into an equation, but most of the times when we do these models and we want to go from, we want to see actually how it goes through population, we can use Excel, just like the CDC. So what I want to do is, for people who are not really familiar with Excel, you're going to have to do this for your homework. I wanted to give you an idea of what is that spreadsheet that you're looking at that Professor Page gave you, and give you an idea of how you actually might be able to answer the homework. There are a couple ways you can do it, but Excel is this wonderful tool, so indulge me for the next 5 minutes, okay? Right. So let's see what we're doing here. So we're looking at the broadcast model, and here's the equation. It's not as pretty, but number of adopters, the next period are a number of adopters now, plus the broadcast coefficient times the number of not yet adopted. And what we're going to do in Excel is we're just going to convert this into Excel language in a second. But you'll see first, so we have a model. We have here a number of eventual adopters, and we have a beta coefficient. All right? Just make this. And so what we'll look at is, for each round, so the first round we have nothing is there. The second round, we know that, I don't know how I do this. So the number of new adopters, you can see, are B4, N. So I'm just multiplying the total number of eventual adopters times B5, the beta coefficient. We see how, like, for the first round, that makes sense. So, because it's actually, there's no, I thought she'd bad. Let's start with Excel. This one's going to confuse you. Oh, yeah. So it's the same thing here. So we're in the next period, and we have, in this period, we want to look at the number of newly added. So we're looking at this part. We want to multiply the beta coefficient, and so we do that here, B5, right, times, little star, the number of total adopters, eventual adopters, minus the number of current adopters. And we get the current adopters in the last round there. You see how that happens? So this is just translating, this part of the equation into Excel speak. Do you see that? Do you see how that happens? Does that make sense? Ish?
What did you get the 5 with the B? I'm sorry. You said
Okay,
B5.
So what we do in Excel is we have to give it values, right?
Okay, yeah.
So here I've just said, okay, I'm gonna, we could do anything here. So let's just do, I'm gonna say 1,000. All right, so we have total number of eventual adopters. We're gonna say, and this is 1,000.
Okay.
Right? And then we're gonna do a beta coefficient. Let's do beta coefficient of 0.5. Okay? Right? And so these are the two things that we need to know for our broadcast model. And we house them in these cells. This is B5, or B5, right? So wherever you want to use the beta coefficient, you put in B5.
Okay.
Yeah?
Yeah.
And then we know, so for a number of new adopters, we know we need the beta coefficient, we have that. And we have to multiply it by n minus nt. Well, n, big N, is in B4.
Oh, okay, I see. Yeah. You're just categorizing
Yeah,
pieces. Okay.
exactly. So we're just translating this into Excel speak and giving it the different coefficients. Is it making sense? Yeah?
Yeah.
So here in this, so in this block, and in all of these blocks, we want to tell it, give us the number of new adopters. Y'all with me? Yeah? And then here we want to say, okay, now give me the new total. So you can tell me, how am I going to get the new total? What do I want to add?
The previous total to the new adopters.
Yeah, I want to add this to this, right? Y'all see that? Previous total plus the new adopters, I'll get the new total. And that's exactly what we have right here. We're adding E5 to F6. No, F5 to E6. Yeah. We're adding this E6 to F5. Cool? And so the really nice thing about Excel, then, we'll show you, is that you don't have to do this 10 times. You can just highlight those things and say, okay, now just keep doing that. Yay. Is that nice? One thing to look out for, so the really nice thing is here, E6 and F5, we don't want them to be the same, we want them to shift each time, right? Right? So Excel knows to do that, we just leave it like this. However, we don't want our B coefficient to change each time. We want it to stay there. If you want something to stay in Excel and not move, you put dollar signs in front of it, and it doesn't move. Cool? All right, now you guys are Excel geniuses. All right, so let's say you want to compare two models, or two cases, I should say. So you want to compare the case where you have n of 1,000 and beta 0.05, and then let's say you want to compare that with when n is 5,000 and beta is 0.7. And you want to be able to answer the question that you need to answer for your homework, which is, when are you able to tell the difference between the two models, right? How are you going to be able to answer that question? You can just go back and forth. Let me see, there's that, 1,000, 0.5, right? You just could go back and forth a couple times, right? And answer the question. What else could you do?
Set up a new model, or set up a new graph.
Okay, you could, right? On a different sheet?
Yeah.
Or you could set up a new model on a different sheet, that's great, and then you can compare them, that's an answer. So here's one other thing you can do. You can put them on the same graph. All right? So I'm just going to show you, quickly how you can do this, in case you want to try it for your homework. It's really not that bad. So here I have case 1, that's called case 1. So I want to do another one, case 2, and I'll put in different quotients. So let's do 1,000, let's do 2,000, and okay? So a quick and dirty way to do this is say, all right, here's this model here, all right? I'm just going to copy and paste. I'm going to copy and paste. Put it right down here. I'm going to call these 2 so that I'm distinguishing them. All right, so just copy and paste. So, it's not quite what we want. I mean, we have to make some changes. So one thing that we have to change is when we go in here, this is actually bad. I should corrected that. Here, we have to correct. We have the wrong. We have the wrong N and B here. So actually, you know what? I'm gonna. Because I'm sure Professor H says this. This is. Oh no, actually, that's not actually. I take it back. So I'm lying to you. All right. So here we want to put in. The N and the new N and B. So the way we do that in Excel is we start with an equal sign, and then it's really nice. You can just click on the new N, and then multiplication is a star, and the new B. Ta-da! Great. Cool. Now we have still a problem here though, because we're referring back to the old B, and we want to refer to the new B. So we have to change this to what? What do we want to change that to?
B7.
B7?
B8.
B8. Great. And this one, yeah, we want to change this one to B7. Great. Here, oh, this looks good, right? This is fine. Right, because it's referring to the right lines, right? So then we take this, and we do the same thing we did before. We just drag along, and ta-da! You have your new model. You have both cases in the same graph. Is that nice? All right. You might not be able to do that for homework. This is an option. You can do the other way we said, just create the 2 in different graphs and look at them and compare them. But if you do it this way, it's going to be much easier to do a comparison. All right? And then you might have another creative way to do it, but this is one way to go about it. All right. Mystified? Do you think you could make, yeah? Any questions on this? Yeah, Brian?
Could you just go over really quickly what the lines correspond to in the graph?
Yeah, so you know what? So I'm gonna, because this, if you actually do it, I recommend, you can do it on Excel and, on your laptop, but this is so nice. I just discovered this, it's like, whoa, I didn't realize how nice Google's spreadsheets are. So in Google Spreadsheets, you do this in Excel, you highlight the data that you want to present, and then you insert a chart, and you can choose over here. This looks crazy, and you're like, whoa, that's not what I wanted, and that's because they switched the rows and columns. All right, so switch rows. So, and then what's really nice here is, I love this program. It asks if you want to use column C as headers, and you say, yeah, thanks. All right, and so now you see this is the total for your second case. This is the total for your first case.
Wait, how did you get to that page again? To click at C as header. Sorry.
Yeah, let's do that again because it's just gorgeous. Sorry, I'm just going up here.
Oh, okay.
Okay, I just got rid of it. So let's do it again. Highlight the data that you want to put in the graph. Insert a chart.
Oh, okay.
Pick the chart, kind of chart you want. Say, whoa, switch the rows and columns, please. And then this does this nice. Please use those headers right there. Okay. All right. I'm not expecting you're going to be able to do this for your homework, but I thought I'd give you this as an option. Yeah.
The one that, like, there was one in the resources, that's already set up, right? Like, for
Yeah.
us to just
So exactly, what you're going to get for your homework is it's already set up. Let's see, I can use that. What you're going to get is he's going to give you one case, right, with one set, and you can either do what you did before. So just put the numbers in the boxes that he's already provided there and see what changes, or you can set up two cases on the same graph. Cool? All right, so this is so you can try that, or you can eyeball it, but if you do it this way, I think you don't have to do it this way, but you might try it.
Okay.
So the other thing is, all right, we'll get there in a second. All right, so we spent a lot of time with the Excel, but I think it's worth it. Let's just go through the other models really quickly. Diffusion model. Instead of having a broadcast rate, we have a rate of how often people in the population meet each other, and when they do, how often they actually transmit the behavior or whatever it is they're transmitting. And in this case, the new adopters are a function of the contact and transmission rate. But we're not just multiplying by the non-adopters. We're multiplying by the non-adopters by the adopters. So let's say these 5 people have adopted already behavior, and then we have 9 people over here. So we have 45 possible interactions, right? 5 times 9. But you guys aren't all going to have 45 interactions. You're only going to actually contact each other maybe, a tenth of the time. So 4 or 5 people, every 4 or 5. There's the chance that you actually transmit, and then you have the new adopters. And just like with the broadcast model, the total in the next round is really just the new adopters plus the old adopters. Cool? These slides will be available. This is what you have for homework, the BAS. And BAS is just saying, in reality, we don't just get information from CNN or just from our friends. We actually get information from our friends and from CNN. So all the BAS model does is, this is the equation you got. If you multiply it out, you realize it's just the diffusion model plus the broadcast model. That's all that is, right? See that? Yeah. And just like we did 2 times 4, you have the new adopters. Oh, not yet. Oh, yeah, here it is. This is the new adopters. And then total adopters are the new adopters plus the old adopters. Right. And then finally, okay. Oh, so this is what you're doing for your homework. You're using the BAS model. That's the one you have. I have a suggestion. So this is the homework that you were given. My suggestion is that you don't do this homework, but you do this homework. So for the second case, make a million, not 100,000. And the reason I suggest that is that you get a much more interesting answer, I think. Okay? That'll be kind of cool. All right? You can do this homework. If you do this homework, you'll be more like, okay, that's cool. All right? So I suggest you do that homework. Got it? Great. And then finally, the SIR. This is used for primarily, or not exclusively, the transmission of infections. It is the diffusion model, plus we add, that understand is people actually recover. They don't just adopt and stay sick, they actually get better. So we have to subtract them out of the model. So it's the rate that adopters recover. Okay? So you got these 4 models, Ruby tunes. And the interesting thing here is what happens when the contact transmission rate is greater than the recovery rate. Is that right?
Tread flies.
Exactly. You'll have an epidemic. It'll spread pretty nastily. And another way of saying this is just divide both sides by A. And so another way of saying it, so it's CT is greater than A, or CT over A is greater than 1. The same, right? You get an epidemic. Questions?
A little bit. For our modeling notebooks, do you want us to do one for each of the different models? Do you want us to do one, just put it under like variants or whatever?
Yeah, for Monday, you got slammed with a lot. So I would put all the adoption models, the ones that we just ran through, together, yeah, in one notebook. It's just, I think that makes most sense. You might want to do a short and dirty one on the ovation model, which we're about to do, because it is kind of different. Yeah. I think it would be hard to make sense of the ovation model. It would be hard for me to make sense of them in the same notebook entry. So just do a short and dirty one on the ovation model so it's clear in your head. All right, and that's what we're going to do now. Yay. Unless there are any more questions on this. Okay. All right, standing ovation. All right, so this is what we got in lecture. You go to performance, and there is a true quality of the performance. This is the way I found this thing. Right, there's a true quality. But everybody sees something else. So they see the true quality plus their like particular kind of whatever, fuzz. Right? So some people see better, some people look worse. Everybody stands if the signal that they get is above a certain threshold. So each person will stand if their signal is above a threshold. But they'll also stand if a certain percentage of the audience stands. Let me boil this down very simply. So in other words, if the true quality plus my error term is above a certain threshold, I will stand. Or if I look around and a certain percentage of the audience is already standing, I'll stand. So these will be the two things that make me stand. Gotcha? That clear? That clear? Great. So let's play this out. So this, what I'm showing you is here is this is the array of possible perceptions, right? Of the quality, perceptions of the quality. So, and let's look at an example where the true quality of a performance is 50, but there is an error of 20. So that means among everybody in the audience, people are going to perceive the quality as anywhere between 30 and 70, right? So this part like disappears, and we're just, the universe of the audience is in between is here. Got that? So let's say the threshold that people stand is 60. So can somebody tell me if everybody perceive, oh, and one more thing. The distribution is uniform. So which one is uniform distribution?
Lower left.
Okay. Often you see this as a this proper distribution. So then it's uniform, so it's just flat. So it's equally likely that you will perceive equality here as perceive equality there. Okay? That makes sense. All right, so in this world where the true quality is here, the error goes from 30 to 70, and the threshold is 60 at which people will stand. What percentage of people stand? Okay, I get your instinct. What you're thinking is people between 60 and 70 stand, right?
It's me.
Oh, is that you?
Sorry,
Emily?
yeah.
Okay,
so-
so you're in the right area. So people in this block are going to stand. What percentage of they are the total population, the total audience?
25.
Yeah. Y'all see that?
Can you do that one more time? Sorry.
Yeah, okay, good.
Just like all the way through, like.
Yeah, okay, great. So, you go to performance, and this is the true quality of performance, 50.
Okay.
But among all, let's say y'all are the audience, some of you see it as a 30, some as a 70, everybody is in between, uniformly distributed. In other words, nobody sees it as a 20 or 10, nobody sees it as an 80 or 90, okay? Everyone sees it between here, and it's uniformly distributed. Everybody who sees it above the 60, so these guys stand. Right? These guys stand. What percentage of these guys are of these guys?
25.
Yeah, 1/4. I mean, 1/4 or 5%. Ruby? Any person?
Does this, so will we be looking at, say my, I guess, threshold for other people standing, like the percentage of other people standing before I stand is different from somebody else's? Are we looking at that at all? Because like my percentage might be 10%, but if, like, 20% of other people's percentage of 10%, then all of a sudden we have 30% of people standing, and then.
You should take an agent-based modeling class and you can do that. Yeah, so exactly. So this actually, the standing ovation model that we're presented here is real basic. It doesn't
Okay.
really represent reality, right?
Okay, so we're
because
assuming
we
that
all
everybody-
don't have the same threshold, right? Yeah?
Okay, that's just.
Yeah, so
okay.
really good. Yeah. So really good. So, but good to point out, this does not represent reality. This is the most basic ovation model. But we could probably imagine that we would want to tweak it. Okay, so good. All right, so let me just throw the last bit in here. Let's say in this instance, X is 30%. In other words, this is the amount of people who need to be standing in the auditorium in order for Deshawn and Emily and everybody else to actually stand. So if they perceive at least 30%, they will stand, okay? If they perceive 30% standing, everyone will stand. So in this model, let me ask you again, how many people stand? In this case, how many people stand?
25%.
Okay, we're still at 25%, right? So we've not hit the threshold. You guys got it? Great, let's try it out. So can you now, there are all slight variations on the one before, with the person sitting next to you. So, two, perfect. Tell me how many people stand in each of these scenarios, okay?
So it goes to like 80.
What is the first new one? Okay, I'm still. What is the X?
The X is the perceived, like if the X is greater than 30% standing. Oh no, then shift, so X is like the threshold, so if in the second one, if the percent we get of the people standing is greater than 30, then everyone stands, but if it's less, then only the percentage that we got.
Okay.
So,
Okay, so for the
Q plus, so the first one,
everybody.
So Q is
So the signal is
and then
whatever it is. Alright, so 70. So the signal is 70 because it's 50 plus 20. The threshold is 60.
Next one.
You can tell me if I'm wrong.
yeah, but then only
60 now.
So the key
from 60 to 70 stands. Is the thing.
But it's greater than the threshold.
Oh,
Oh, from 60 to 70.
Yeah, I think.
Less than.
And which is 25% of the overall.
25%.
Yeah. So then the next one is 50 to 80. So then between 60 to 100%. And so then between 80 and 100 there's how many? 5. So 2 of 5. Yeah. So then they do stand, so then everyone stands, right? Hey Julia.
Alright, so can we see why that's half?
Oh, yeah.
I have a question, but it's okay.
Are you sure?
Yeah.
I don't know, I feel like we should make sure we're doing this right.
Yeah, I just, okay. So,
Okay.
well, we'll score it. I mean, like, it doesn't matter.
Alright, so
I was literally like looking at other people like that.
And 50, so nobody stands because
Not like a standard.
so it's 40% of the way to do that.
I think so. I mean, like, I'm not really sure. But it's the same value. So.
They just had to stand up, but everybody else is like, no, I don't have that low threshold. Because I saw you. Alright, so then the next one, we had 90.
I was
Oh yeah, I saw you.
yeah, but I turned it around.
The error is 30. So max at
I just wanted to make sure that everyone is in.
Yeah, another way.
you go $30. You go any.
Oh, I've been keeping up so far. I was
3 of 6.
Not do 1 and not do 2.
Great, let's see what we got.
Yes.
No,
So did they.
So they
Alright,
stand.
so, how many people stand
be.
in
This is
this
greater
case?
than.
All.
Lovely, in this scenario? 1/3. Okay, great. Is that good then?
No.
No.
Okay, what did you guys get here?
But I think we're doing it wrong, so.
Did you get 100% here?
No. Yeah, so we're doing completely wrong.
Wait, what were we supposed to do?
Alright. Maybe we'll start on Friday after.
Yeah.
Oh, you work tomorrow, sorry. I can actually hang around after class.
Okay.
Okay.
Yeah.
So we move on. Here?
Wait, that's.
Oh, we already did that one, okay. Everyone, yeah?
Yeah.
Okay, good. Alright, well, I'll stick around. Alright, cool. Nice. So you'll be playing around with this in your homework, and so you guys can handle it. Any more questions on this? Alright, now let's spend some time going over coordination games. Professor Page asked how many people are familiar with these, about half of them raise their hands, so I just want to make sure everybody knows what's going on here, right? Okay, so this is a pure coordination game, and all these games are set up the same way. We have 2 players. This is the example of players 1 and 2 can put their ketchup in the fridge or the cupboard. So player 1 has 2 choices. Player 1 can choose fridge, get these options, or cupboard, get these options. And whether he gets, he chooses fridge, and he has these options or these options, depends upon what player chooses. So if player 1 also chooses fridge, they both get a payoff of 1 for player 1, 1 for player 2. If, however, player 1 chooses fridge, but player 2 chooses cupboard, player 1 gets 0, player 2 gets 0. Cool. So one of the easiest ways to figure out what do people do besides saying, well, it's obvious what people do, because sometimes it's not so obvious, is to think of it this way. Start in any square and ask yourself, do the players stay there? So for example, we could start here where player 1 chooses fridge and player 2 chooses cupboard. Now if I'm player 1, if player 2 chooses cupboard, I am only dealing with this reality. Does that make sense? Because I'm player 1, I can choose go up here or go there. I can't go this way, I can just go this way. So if player 2 is in the land, has chosen cupboard, these are my 2 choices. So let's say I'm here, I've chosen fridge, player 2 has chosen cupboard, so we're both getting payoff of 0. I can move to here, in other words, I can start using the cupboard. Do I move from here to here?
Should.
And so if you have if you're homo economicus, so if you behave the way economists think you behave, you would, because you're going to get a higher payoff, and people will always take the higher payoff. Okay, make sense? So that's really clear, right? And then conversely, like if we're both here. So let's look from player 2. So player 2, let's see, is here. So player 1 has chosen fridge. So player 2 says I can be here, here, I'm here. Am I going to change the cupboard? Because I would never take 0 over 1. Yeah?
Does this game assume that we know the other person's action then?
So what's nice about these, oh yes.
Okay.
Yes, yes, yes. So I know that I'm here because I'm using a fridge and the other guy is using the cupboard.
Right.
I know I'm there. Yeah, exactly.
So it's not like a prisoner's dilemma where they're like in 2 different rooms, like separated, and they don't know each other's situation.
Yes. Well, yeah. So the prisoner's dilemma is different from this. Right, because they're right. Yeah. There's a significant answer to that because there's a dominant choice, which is that it doesn't matter. So if I'm a player 1, it doesn't matter to me what this guy is playing. I'm always better off choosing cover. So that means this is right. So this is always going to be better, and likewise for player 2. So which is different here because there isn't a so there's actually ambiguity here, but let's say we both know we're in this thing, okay? So now things get complicated when we go here. So if we think about it, going back to this option, let's say I'm you, or me, let's say I'm me. And so I have chosen the English system of keeping track of weights and measures. And my friend has chosen the English system as well. All right, so we're both in this land. So my friend has chosen this. So my options are, I can be here or here. Am I going to convert to the metric system? No. Same thing with my friend. I'm the English system. He can go here or here. Is he going to convert to the metric system? So we're both kind of locked in this suboptimal world of ones and ones. If we could think of some way to coordinate us where we could both make the leap here simultaneously, then we could go there. But we're not going to do that making individual choices. We have to somehow be compelled forcibly by the state or something to get us here. Does that make sense? It's not going to happen on its own. Whereas if we were, but if we were here, it could happen on its own. If we were in this area, then we could see our friend would say, oh wow, I'm using this crappy English system. My friend is using the metric system, I might as well should convert. But from here, we're not going to get here. Make sense? Right? Okay, cool. So, any questions on this? So let us, for your homework, you have to come up with some examples from your brains. So I figured that was kind of hard, so we'd spend some time working with pairs. So I'd like in pairs for you guys to come up with one pure coordination game where it's kind of like it doesn't matter where you end, and one dominant one where there is a better outcome, but it's possible you can land in this crappy place, or you can land in a really good place. The way I interpret this, you have to look for like a good and bad, is the way I interpret it, and there might be another interpretation to this, which is you want to think about, in reality, in the world as we know it, is there any time we're actually here? Where we, could theoretically be here, but we're not going to get there. Does that make sense? Versus at any time in the world where we're actually here. Yay! Okay? All right, and you can, so think of one pure coordination and one dominant. Cool? And back in your pairs again. And and for your homework, you can use one of the ones that you come up with today, but you don't steal from others. Not on the honor system like that. Cool? Right.
But real life examples, or real world examples.
Yeah, exactly.
What's that?
I know, that's hard, huh?
I mean, this seems rather straightforward.
Flipping a coin. If you both fall the same week, then we watch like different and then if we watch, then we'll be together and do the we watch movies separately.
That's a good one.
Yeah.
Do
Do you guys want to go over ovation now, or would you play around? Want to play around with this? Do you have 5 minutes after class?
Yeah.
Okay, then let's do that.
But I like that one. If they will choose
Alright, so
Yeah, it's like you have some didn't know there was a South Quad.
It's really good.
So he kept going to South Hall. It's like, dude, Gary.
You keep this up.
I don't know where South Hall is.
One second. So I didn't actually look over all of your Markov model notebooks. I'm sorry, I haven't. Whatever. But I'm going to hand them back to you. If you've got to check, that means if you continue to, if your model notebook looks like that, you'll end up getting 13, 14, or 15 out of 15 points. So you're on the right track. Keep up good work. If I wrote a note for you, you can come see me, or if it's not clear what my notes are, but you want to clarify some things in order to get a high grade on your model notebook. Okay? Continue.
Wait, let's do the day of the midterm, or is it the midterm?
Do you have my stuff from the previous section? Do you have my stuff from the previous section? Because mine would have been in that pile, because I just switched out of the other section. We can just give it after 5.
Yeah, just like
yeah.
We each would have South Quad.
There was one
I mean, the format isn't the same.
Right side inside the whole you work on your
So you have 5.
But the road system so it was like people are walking wrong way and then something like that, and then one day
I have no idea what I'm doing, so
alright, I'll take it. Tomorrow we will switch how everywhere walk. Yeah, it's not of course on the road like
see, I'm gonna ask her about it, because I like.
it's not like only people walk this way, walk there. Like they're like all like mixed, but inside of the building there's stairs.
Yeah.
Kind of weird. So.
Interesting, it's like 2 different coordinations.
Yeah.
That's really interesting. Because just do my own and we walk.
Yeah.
It's like culture for smell, it's very confusing.
Oh, what's right?
Let's start off with Barry just asked me, putting you on the spot. Was wondering if one worked. You want to ask the group and see?
So you can either choose oil, using oil, or alternative energy. If you both pick oil, you get like a small like short-term payoff. If one of you picks alternative energy, one of you picks oil, you get no payoff because there's no long-term effect to the environment.
Oh, okay.
And then if both of you pick alternative energy, you get a long-term, bigger payoff in the future because the environment is better and such. And energy is cheaper.
Oh, okay. So that's the last part. So, so the idea is that I guess if everybody chooses, we want everyone to use electricity. Or use, sorry.
Also alternative.
I'm thinking of cars. We want everyone to use alternative energy instead of fossil fuel energy, right? And so there's going to be some added payoff for all using alternate, which is what?
So if we're all using, so if both of you use oil, so you're both in the oil thing, then you get a small term payoff because
Gas is cheap.
yeah, I guess somehow gas would be cheaper if we all used oil. Yeah, gas would be cheaper if we all used oil. If one of you uses alternative energy and one of you uses oil, I guess there's no payment payoff because there's no like demand suppression. So like gets into economic principles, which makes it difficult. But if both of you use alternative energy, then I guess alternative energy becomes cheaper in the future than oil is now.
What I like about what you say is that there might be some net payoff to all of us using alternative energy in terms of the environment. But what you're assuming is that we only all get that benefit when all of us are using it.
Yeah, that's what I was
But what you might actually think, so pushbacks, this is actually very complicated, we started with really complicated now. It might not be the case, because you could imagine every time somebody converts to fossil fuel to non-fossil fuel, we might just have an incremental benefit. So we might actually have a linear thing. It's not like once we all convert, it goes like that.
Right.
But we start off with really complicated stuff. I like your ambition though. Okay, does someone have another example of a, let's say, pure? Yeah, Ben?
I think this one works, but you guys can tell me that. So, I think for a period of time in like the 70s or 80s or something, the drinking age in the U.S. was changing from 18 to 21. And for a period of time, if I'm right, it was a state-by-state basis. So, like what I thought was, it doesn't really matter if the drinking age is 18 or 21, as long as all of the states have the same drinking age.
Okay.
So if option 1 was drinking age 18 and option 2 was drinking age 21, that means in terms of like, you know, drunk driving deaths or something.
Why would it be bad if it was different?
Because that means that you could have, you know, people going state to state and breaking the law inadvertently, or I don't know. People.
All right, so it might be bad because you would have people rushing from New Jersey and flooding into New York on weekends. So 18 to 21-year-olds. So it would be bad for New York because there would be this crazy influx of 18 to 21.
And it could be bad in terms of economics if people are going across state boundaries to buy alcohol or something.
Right. That example, which is close to home, I was just missed being grandfathered into drinking at 18. I was like 17 when they changed the law, and 18-year-olds are grandfathered in. I was torn. It was awful. Okay, let's do it. It's so cruel. One other yeah, Natalia?
I was thinking that when like political parties kind of bus people to the polls, so if they didn't, then maybe they wouldn't get the vote. So they, you know, they bus people and then they get the votes, or they don't get the votes. Or like one political party buses people and another one doesn't, and they get the votes for that for a year, maybe not.
But so why is it better? So you think it's better if they're both busing or both not busing?
Well, I mean, I'm thinking like if one doesn't, then the other one will kind of, maybe I'm thinking more prisoners dilemma than one nation game. Because like if one doesn't and the other one does.
So you guys are getting really sophisticated really fast. Do you have a simple one, Matt?
I was just gonna say, like, both the alternative energy and the oil one and this one could be solved if you just say like societal benefit, because society benefits if more people vote. Society benefits overall if maybe it only benefits if like alternative energy prices are cheaper, whereas it also benefits economically and.
Okay, so I think you're right, but I think what you want to get as a distinction is that because with all those, if I convert to natural energy or if I vote, right? So each person who converts, it gets better. But the idea here is that it only gets better when we all do it, which is the difference. Yeah. So do you guys get that? So it doesn't matter. So if I'm voting and somebody else isn't voting, then we're all screwed. That's not the case. If I'm voting, so it's a little bit better than both of us not voting. You see what I'm saying? So the case it's only good when we both do it. There's no benefit if only half of us do it. There's huge benefit if everybody does it. So that's what you want to be thinking of. Yeah, you got one?
I have a question.
Yeah.
So the payoff determined is based on population, not on benefit? Because I thought the payoff, because like what he was saying like made sense, like because if you have like a really high benefit from something, even if you just count it as one, you have like a low benefit from something else, like a 0 or a -1 or whatever. That would make the graph do that 90-degree turn to the left, you know?
Yeah, so when we jump to populations, you think about this. So it's not 1 and 1, but if you think that if half the population is here and half the population is there, it's a mess. If half the population is driving on the left side of the road and half the population is driving on the right side of the road, it's a mess. All right? If we all drive on the left side of the road, yay! If we all drive on the right side of the road, yay! So that's what you want to think about. When do you only get the benefit? When we're all doing it. That's what you want to be thinking about, okay? Does that make sense? So a very simple example, actually someone came up with last class, and it's also an iconic example. If you are meeting a friend for dinner, you either both want to be at Silvio's or you both want to be at, Lena's. You don't want one of you to be at Silvio's and one at Lena's and the other, right? The other, okay, exactly. So you guys are getting really like social scientists, like sophisticated. Maybe bring it down for your homework and think of this like very simple, like where are you putting the ketchup in the cup of the fridge? Okay. So play around with those. Really good work. Thanks.